Hello, I'm Efthymios Sofos. Right now I'm in Max Planck visiting for a few months. I do number theory and my current university is in Glasgow. So before that I did my PhD in Bristol University under the supervision of Tim Browning and Andy Booker. I finished in 2015. I guess, and then I traveled a little bit. I went to Leiden for 2 years, and then I came to Max Planck to do a postdoc for 2 years, and then I moved to Glasgow in 2019. So during my PhD with Tim Browning, I was interested in Manin's conjecture. So this is a conjecture made actually by Yuri Manin, who was here in Max Planck. So take a Diophantine equation in quite a few variables, like 4 or 5 variables in small degree, and then the question is, whether you can solve these in the integers, but whether you can count the number of solutions in specific boxes. And Yuri Manin in the 90s, together with his collaborators, realized that there are some geometric patterns that appear. So for example, the rank of the Picard group appears in the asymptotic. So this was quite new. And in my PhD, I worked on some cases about cubic surfaces and Del-Pezzo surfaces of degree 4 and degree 2. And so when I was in Bristol, there were many people visiting all the time, like collaborators of Tim, other postdocs and students. So one of them was Dan Loughran, and at that moment he was interested in an old paper of Jean-Pierre Serre from 1990. I guess when he was visiting here and he was talking to Manin, there's this little note. So Jean-Pierre Serre wrote this paper about the following thing: take an infinite family of random Diophantine equations, then you can ask, does it have a solution in the integers 100% of the time? Or can we know, for example, with the Hasse principle, whether it can have a rational point for 100% of the time? And so I guess Jean-Pierre Serre was visiting here 91, 92, and they had this discussion with Manin, and Manin asked him, what about the case when you have a planar conic diagonal? So when you have 3 integer coefficients in a box, how many of these conics have a rational point? And then Jean-Pierre Serre wrote a paper where he generalized this to like a lot of families, Brouwer-Severi varieties to be precise. And then he wrote this paper in the 90s, but it was kind of forgotten. And then Dan Loughran around 2013, 2014, he resurrected the subject. It was also in fashion, coming from the team of Manjul Bhargava, where so Manjul was doing, like, take a random elliptic curve, can you figure out what is the average rank? Or can you bound the Selmer group in a way? And so all of these were in fashion. So I was then interested in this topic for a couple of years. So random Fano varieties. And then when I did my postdoc in Leiden, there were a lot of strong students, like a very big list, some of which I have collaborated quite a lot. And 2 of them, the very, very strong students, Carlo Pagano and Peter Koeman. So they were doing Cohen-Lenstra heuristics, and they taught me quite a lot, and we've written some papers since then. So this is about taking, let's say, a random quadratic number field and asking some statistical questions. For example, what is the average size of some part of the class group? And after that, I guess, when I moved to Glasgow, I started being interested in more analytic questions. So for example, there's Sinchel's hypothesis. This says, take an integer polynomial like x squared plus 1. Does it represent infinitely many prime values? This is still quite open. And in fact, this question is open every time you have any reducible polynomial of degree bigger than 1. And because this has a lot of nice applications to like different topics, because it's very fundamental. It's about polynomials and primes. So for example, Coyote-Len and Swinnerton Dyer in the 70s and the 80s, they understood that you can, if this conjecture about prime values of polynomials was true, then you would be able to prove that the Hasse principle holds for a lot of interesting surfaces that come up naturally in geometry. So Del-Petro surfaces, for example. And so I started being interested in the analytic part of these questions. So I proved this result that if you have a random integer polynomial, let's say of degree 3, then with probability 1, it satisfies this hypothesis about representing prime numbers. There was a trimester program in Paris in 2019 organized by Emmanuel Per, Harari, and Skorobogatov. And there were many very interesting short courses. One of them was by Jonathan Harpas, and he was describing how you can push this idea I talked about before, this using Sinchel's hypothesis about prime values of polynomials, how you can push this idea to prove the Hasse principle for very difficult surfaces, like for K3 surfaces. And it felt to me that almost every other course was about, let's assume this analytic conjecture and then prove this nice Hasse principle statement. Now, at the same time, I had a master student who was writing a thesis in Leiden. It was on the Vinogradov theorem on 3 primes. So every large odd number is a sum of 3 primes. And the same proof shows that Goldbach's conjecture holds 100% of the time. So Goldbach's conjecture says that if you have any even number, then it is a sum of 2 primes. And already Hardy and Lilhood realized that under the Riemann hypothesis, you can prove that 100% of even integers are indeed the sum of 2 primes. And it's kind of the same proof as Vinogradov. And actually Vinogradov made also this 100% Goldbach proof. He made it unconditional. So my student was doing that, and then I remember I was in this lecture, sitting at the back at this very nice small amphitheater in Institute Henry Poincaré. So there was this course about Sincel hypothesis, and then in my mind it clicked immediately that what you should be doing is average over all integer polynomials, let's say a fixed degree, take a random polynomial and then try to prove that it represents at least one prime number. And then this would give very strong implications for rational points on surfaces. Yes, so the kind of applications are typically on surfaces for which there is very few things known unconditionally. So for example, cubic surfaces are supposed to satisfy the Hasse principle under the triviality of the Brouwer group, but it's not yet completely, it's not proved. So these analytic methods and the random polynomial methods, they were towards questions like that. Take a specific random family of surfaces and try and prove nice things about the existence of rational points. Yeah. When I was little, my parents thought it was an amazing idea that I start playing classical guitar when I was 5, because my uncle is a teacher. So we had 3 courses, and what's wrong with that? So I got the conservatoire degree when I was 21, and since then the music bug has never left me. So now when I work or when I walk or when I do anything at all, even when I sleep, there's background music playing, and I associate every period of my life with a specific kind of music. So for example, when I was doing PhD, I decided I should listen to all the music made by Miles Davis, John Coltrane, and Bill Evans, and I was interested in their lives as well, so I bought all the biographies there are, I read it all, and yeah, so the catalog of Miles Davis is quite huge. I mean, it's more than 100 records. And then before that, when I was in high school, for example, I was playing in a rock band, so I listened to all the British rock music from the 70s and the 60s. Then when I started my postdoc in Leiden, I became again obsessed with classical music. And Yeah, of course, the beginning and the end of all music is Bach, and I decided to listen to the whole catalog. It's, I don't know, like how many hundreds and hundreds of hours of music. Again, I bought all the biographies, I read them all, and yeah, so lately I have been listening to a lot of gypsy jazz. This is like Paris style guitar jazz. And yeah, so this music is always like a permanent interest. I always love listening to music. I guess like many mathematicians. The other interest I got lately, specifically during COVID, there was this like quarantine, and I decided what I should be doing is like learn a bit about art. So I took a couple of courses in Glasgow University about art, Baroque painting to be precise. So I learned a bit about Ribera, Caravaggio, Artemisia Gentileschi, and architecture in Baroque times. And then I wrote a little thesis about Spanish painting. I don't feel I'm in a position to give any serious advice. But in my area, I've got some very useful advice. I can tell you some of it. So specifically, this is suitable for analytic number theory. So one piece of advice I got is you should keep like a very long list of open problems and like ramifications of these open problems or like closely related questions. And then you should also keep a big open list of new techniques, preferably techniques that not many people understand and that are kind of like new, like in the last 1 or 2 years. And then every once in a while you should try and mix them randomly, so to speak. And then it almost never works, but all you need is 1 in 100. And yeah, so I do not pretend I follow this advice very closely, but yeah, I think it's a good piece of advice for topics like combinatorics or like analytic number theory and stuff like this. I've been here a couple of times. The atmosphere is hugely inspiring because this place has massive history. So the minute you come in, you are automatically inspired by all the people like Don Zagier and Peter Solze, and Yuri Manin was here, Hirzebruch, Foltings. Yeah, so it's impossible to think anything else other than mathematics. The other thing is that there's a big support for people traveling from all over the world. So every week there are different like professors from all over, like America or Asia or Europe. And even if you don't talk to some of your mentors or some of the collaborators, you can always talk to all these visitors, and it's always nice. You make connections, and it's like impossible to not start writing papers with them. And the other thing is that so when I was a postdoc here, I spent a long time, around 2 years, I guess. So what I noticed is that the professors that are here are extremely friendly, and the door is always open. You can always send an email and discuss math or anything else that you want. And specifically, I remember Yuri Manin, we were always discussing about things, well, not about math, but architecture and poetry. He had big interest in everything, basically. And yeah, also the staff that works here is extremely helpful. So they will help you with your travel, with finding a house, like with bureaucracy. Like I cannot imagine a better place to do mathematics, and especially for a postdoc, and everything is like exceptionally well organized. And here you can come, like that's the feeling I had. You can come and just do math. There's nothing else. There's no admin. There's no teaching, and everyone takes care of you. And it's like you come here and you forget about everyday problems, and you just write papers and collaborate with all these hundreds of visitors.